Alright, welcome back to another video by Firestarter Graphics and Engineering. Today we're going to go over a little bit more advanced FEA analysis. When I say advanced, this is actually kind of some basic intermediate things that we should be doing always when we do FEA, but when you take a course on it or you learn something on YouTube about it, they don't go over this section. So I'm going to do that. So last time, you remember, on one of my videos, we took this airfoil shape. I gotta find it. There it is. Woo! Okay. Took this airfoil shape, we traced it, and then made about, I don't know, 13 sections or so, maybe less, scaled each one to its appropriate scale factor, and then created, let's go ahead and hide that, and created the actual blade. So this is what the completed blade looks like, and you should have seen this in some of the other FBA videos that I've done. So if we look down as if we were looking at a 3D printer bed or just a table, this is standing on its end. You can see the angle of twist, how it's flat against the top, but this portion is angled. So if we were to connect this to the hub, we'd get the angle of twist that we need. Also, if we look at the right side, you can see how it's twisted, and just a tiny bit of twist along this section of the blade. And then we went ahead and did some basic FEA analysis where we made the actual mesh. And don't mind my cats in the background because I'm at the home studio today because we have about 14 inches of snow. I'm not going to drive anywhere. So that's that. Yeah, so don't mind the cats. They're okay. Anyway, so last time we went over kind of the mesh and how to generate the mesh using Gmesh and how to fine tune it until you get what you want. Till at least you get no errors in the mesh and something that works pretty well. You'll notice last time I had a second order and also a first order, and then we moved to a second order, and I said second order is more accurate. That is true. However, today we're going to learn that even with a first and a second order, you can get instability with your meshes, and that's what I want to go over. So you'll notice I'm using a first order. Maximum size is 5, minimum size is 2. That is the size of mesh I want for this particular geometry. I mean, if we look at the edges, we got good coverage. I mean, the mesh looks nice, and if we move to the holes, okay, not too bad. It's going to do what we need it to do. So I'm going to go ahead and hit cancel, and then let's look at the materials. Okay, so I didn't save it. Okay, well, let's go ahead and update these. This should be 3. This should be 6100. You're probably asking where I get these values from, and we're going to talk about that in a minute. Poisson's ratio should be 0.42, and we're going to hit OK. So everything should be good. Then we're going to go ahead and in Solver Tools, we're going to write the INP file. This could take a few seconds, maybe 20 seconds or so. Okay, I lied. It was like 4 seconds. Now we're going to run Calculix, and look, calculates with no errors. Let's go ahead and look at the results. And displacement, negative 127 millimeters. Now, just in case this is wrong, one thing I always like to do first, go to the FEM bench. I will purge the results, okay? And then I'll go back and rewrite it, and then we'll run it again. And the reason why I do this is just in case there's something, I don't know. You never know. But if we look at the results, it should be still the same. Okay, now we can look, and you're probably wondering, wow, 127 millimeters of deflection, and your force is only 200 newtons, which is like 40 pounds, and your force is distributed. Saw me right. And you'd be right. You'd be correct to think that. However, that is the actual correct value, and I have validated it 3 different times, and I'm going to show you how I validated it 3 different times. So, this is where the advanced techniques kind of get in. If you get weird values, the first thing you should do is what we call a convergence study. Okay, so let's go ahead and bring that up. What does that mean? Now, I'll talk about all these equations here in a minute. Excuse me. So, this graph shows my convergence study. How I did it was I took max size and min size of the G-mesh, 7, 2, 5, 2, 4, 2, 3, all the way down to 1 and 1. After 1 millimeter and 1 millimeter, the computational time was so long, and even my 32 gigabyte 12 core CPU supercomputer at home was struggling, and it was just causing issues because of these tinier faces, these smaller faces. Now you got to remember, because we get down here, this right here is not that thick. That's like 0.5 millimeter. So you try to pack more mesh in there, which would be more accurate, yes, so to speak, theoretically. Excuse me. You can run into some serious computational errors as you start running around, corners and stuff. So, best to do this convergence study. And then I graphed. Sorry, I didn't graph yet. I had the deflection, and then I graphed all that. And you'll notice, starting at 5, all the way to 7, and even further past this, the deflection stayed 39, 39, 39, 38. So that is where the convergence is. So I stayed at a 5. I stayed at the smallest mesh size where convergence starts, because you don't want to be too big and then you just get bad results. So that's why my mesh was that. Now, I went ahead and was like, okay, I'm going to see if I can validate this using just a basic cantilever beam. So length of the beam, Young's modulus, Poisson's ratio, the area of cross-section, which I calculated using another calculator. Using another calculator, I got this. Deflection, -146. Okay, that's close to my 127. Then I went into a website that I've talked about before, and I uploaded the blade. This is intact.design. This is where they do meshless FEA. And I exported the STL from FreeCAD, put it in here, did a 200 Newton, same restraints, same force, same everything. Okay, let's zoom in right here. Let's look at the deflection. Total deflection, 88 millimeters. So, and same material, so I know that 127 is pretty close. How accurate is meshless FEA, you ask? That's a great question. I don't know. I have contacted the company and they say it's accurate, but they have other software that's better. But for free software, this is pretty good, they said. And I agree with them. It's pretty good. It gives you a rough guess. So we're anywhere between 90 to 146. Now, I wouldn't really trust this 146. I mean, you can, but remember, this is just based off of a simple beam versus my geometry, which is a little different. That's why, I had to make sure these are as accurate as possible. So that's why I say I'm in between the two, which means I'm probably pretty dang close. Now, you could add up all three and take an average, which would be fine. But I'd probably trust this result just fine. Okay, so let's move back to all of these other things. Now you'll notice I was putting in material properties, and you're probably wondering where I got those. Well, I calculated them, and here's why. Because everything I found online for nylon 66 with 30% carbon fiber varied from 21, like right here. This is the results I got. 21 gigapascals, 19, 5.9, and 1.9. Those were the values that I was getting for the Young's modulus. That's not okay. That's too spread across. So what I did was I took the blade, now remember from previous videos, the blade had been cut into sections. Excuse me. I took the blade and I cut it into a dog bone shape. Now let me show you what that is. Okay, this is a dog bone. It's called that because it kind of looks like a dog bone. And these are the test samples that you put in what they call a tensile strength testing machine. It's got a more technical name than that, but I just call it that because it's cool. So, cut it into this shape, and then we went ahead and put it in our machine, right here. So it's in our machine. And then we did a tensile test. And then we got raw data back, and that raw data gave me the Young's modulus of 6,100 megapascals. Okay, perfect. So, we got that material property. Now, what about density and all of this other stuff? And you're probably, you know, you could, if you're an engineer, you probably recognize some of these equations, especially if you're in material science, you'll definitely know this one. This is called the rule of mixtures. This is the volume fraction. This is really to tell if you really have 30% carbon fiber or 30% of whatever in your matrix. So basically a density of a binary mixture is you take your volume percentage, multiply it of the first thing, multiply it by its density at, very simple formula. So our binary mixture of nylon 66 with 30% CF should be 1.32 grams per centimeter cubed. I get 1.38. Now how I did that was I took a sample of my blade and I weighed it on my jewelry scale, which is really accurate. So I got 18 grams. It was 18.001, so 2 decimal places, I'm calling it 18. Then to find the the density, I used the good old school Archimedes principle of volume displacement. Used a graduated cylinder from one of my experiments I used for chemistry and microbiology class for a paper I wrote. Filled it up to, I don't remember what number it was filled up to, but it ended up being 13 milliliters of displacement. Now with that, 1 milliliter is the same as a cubic centimeter, so you can find your density from there. That's how I got the 1.38. Okay, now using this, I wanted to see how much of it was actually truly carbon fiber. Carbon fiber, if this number, 1.75 grams per centimeter cubed, is correct, if and only if this number is correct, this works. Turns out we have, excuse me, y'all, 22% carbon fiber mixed with our nylon. So it's going to be a little bit more stretchy than it is more of a stiff type blade. Okay, now doing some other test stuff like the burn test. It burned actually kind of quickly. It even burned just cutting it, so I know it's more nylon than carbon fiber. And I know the carbon fiber that they're using is pretty cheap because the blade itself is pretty cheap. So this is most likely like 15%. So that means there's going to be a lot of deflection. Okay. Now, okay, finding Poisson's ratio. You take your ultimate strength, which is going to equal your Young's modulus times your Poisson's ratio times the strain, the ultimate strain, which in our case it was stretched 5 millimeters. So the data timestamps came out starting at negative 108 and then negative 103 at the end. So you just find the difference, which was roughly 5 millimeters. Divided by its original length, and then you solve for V. And when you solve for V, we got 0.42. Okay, so that you can then update your material properties within FreeCAD, and then run the test. So that is basically it. That is kind of an introduction, a basic introduction to advanced topics in FEA. Now there's more to it than that, but I mean, just doing this amount took me probably, a good 20-30 hours. It's not something that can be done within like 15-20 minutes. It's getting this data, making the graph, it's getting these equations, finding the right equations, doing all these things, but also the computational time to run these. Yeah, it was 4 seconds for some of them, but some of them took 20 to 30 minutes as it got smaller and smaller. So, in preparation and the modeling itself took a long time, because even though it's a simple shape, still trying to find the scale factor, cutting the blade, everything that was done for this, I've probably put in 15, 30, 60 hours. 60 hours worth of work. Which, a normal work week, that's 40 hours a week. But you gotta remember, I'm only doing this 15 hours a week because of other obligations that need to be done. So it took a couple of weeks. But anyway, that is the basic introduction to advanced FEA, or I like to call it advanced FEA. Now, if you really want to do advanced FEA, I'll cover that later, but we're going to talk about how to run the Calculix solver right here outside of FreeCAD, but with our mesh generated from FreeCAD, and to do other things like crack propagation and calculating those kinds of things, such as Paris law, which is about crack propagation. And then we can get, from those numbers, we can input it into other simulators and get fatigue life. We could use an open source program called OpenFast and MLife and get fatigue values back. And then we could also use OpenFoam to do CFD, and in that case we need the other model that doesn't have the flat edges, that has the actual airfoil, because this would be a terrible airfoil. Anyways, okay, perfect. Thank you for watching, and I hope you learned something. And sorry for sneezing so much. It's freaking winter here, 14 inches of snow, it's cold, and who knows what the heck's floating around. So anyways, y'all stay safe and have a great winter holiday.